Well, hello again, and welcome to another episode of CISO Tradecraft, the podcast that provides you with the information, knowledge, and wisdom to be a more effective cybersecurity leader. My name is G. Mark Hardy, and I got a special treat for you today. I've got an interview with somebody who's a world-class expert in IPv6. And you need to hear what he's got to say, and we want to explore this topic because, as we're going to see, this is the way of the future, and it's going to happen a lot more in our enterprises than it is today. Now, as always, please follow us on LinkedIn. Make sure you subscribe so you can get the latest updates. Today, I have the privilege of speaking with Joe Klein. He's with Longboat LLC, but Joe and I go back quite a few years and have the privilege to know this person whom I kind of joke about is he's the guy that Vince Cerf goes to when he's got a question about IPv6. So, Joe, welcome to the show.
Oh, well, thank you. It's a privilege.
So, Joe, IPv6. For some people, it's kind of figuring out what it is. Other people are up to their elbows in it. But for our listeners who are relatively new in this area, why would we do that? What's wrong with what we're doing now?
Yeah, so from a business case, the ability to of addresses and ability to modify or reduce our cost of power and processing on our routers and switches, and also be able to support protocols like 5G, zero trust networks, and components like this, IPv6 becomes a really good tool to use as you're going through the process.
So it's really enabling us to get into the business tools and methodologies of tomorrow.
Absolutely. Actually, there's three roles right now. One is that the ability to lower cost of operations, which we've seen it internationally. Those that were early adopters.
Mm-hmm.
Which, by the way, that includes companies like Facebook and Microsoft and such. They basically have reduced latency for going to websites. They have end-to-end connectivity, so they can use that from a security standpoint and an operational and routing standpoint. So this becomes really, really valuable. The other thing is by removing IPv4, the current protocol, you get to actually identify the software and other things that have not only coding, but you also have the ability to fix some of those network problems and some of those application problems that we've kind of ignored over the years. We also have a level of innovation because I don't know if you know it, but Starlink is moving to IPv6. There's lots of protocols that already have IPv6 installed in them.
Mm-hmm.
You just have to enable them, and there's a lot of innovation taking place in that space. So that is really the business case.
So a business case, if I hear what you're saying, is I get some cost savings because I can go ahead and do less processing because I'm able to move things. It sounds like it might actually get some speed enhancements in terms of being able to reach different systems or addresses as the IPv6 space is probably easier to navigate.
Yeah, but you also have things like LinkedIn. LinkedIn saw a latency lowering by 40%
Wow.
once they moved to IPv6.
Mm-hmm.
They moved all their data centers to IPv6 only. Well, if you're trying to do IPv4, you have to go through their proxies, which actually slows
Slows
down the
them down
connection.
then.
Yeah. So, and it makes it really interesting because for 4G, the majority of carriers in the world are running IPv6 because it lowered their cost of operation.
And that's a good point. I know when I teach my classes, I tell people take out your cell phone, turn off the Wi-Fi so you're not running on your home network, and go to ip6.me. In fact, you can do that right now if you'd like, assuming you're not listening on your phone, or you could pause, listen to it, and come back to the podcast. But with IP6ME, it's essentially going to go ahead and reflect back to you, if you have an IPv6 address, the address that you're using. And if you don't have an IPv6 address, depending upon your carrier, it's going to reflect back as an IPv4. So now what we can do is, as I tell people, you're using IPv6 most likely whether you know it or not.
And my concern from a security perspective is this has been going on since 97.
Mm-hmm.
For the first, actually, it was an IBM device that supported IPv6. But we've had multiple vulnerabilities along the way.
Mm-hmm.
And unfortunately, most of the products, if you're not preparing your security tools, your SOCs and such for IPv6, there's a good chance that IPv6 is invisible. The ability to actually detect from a SOC standpoint, from a knock, um, is a real issue. And Microsoft supports for Exchange. They require exchange to exchange protocols be supporting IPv6, and you may not even see this. And that's one of the concerns that you and I've talked about before. Is from a security perspective, it's a must now. It's
Mm-hmm.
not a should.
Yeah, and we find out is that, okay, April 2014. I remember that day because that's when Microsoft said, you need to set aside your XP. But I loved XP. It was the last major operating system that did not do IPv6 by default. Windows Vista 7, 8, 8.1, 10, and now 11, along with Mac OS and Android and Ubuntu, and you name any Linux variant, they're always going to try IPv6 first. So, as you had indicated, if we are stuck in the old IPv4 world because most of us grew up with that, and numbers like 192.168.100.1 sound right. What's the implication of having IPv6 in our enterprise? Because, of course, all these vendors make it work. You can't buy a router today unless it's got cobwebs in it that won't handle IPv6. But what's the implication if we're not looking for it?
One is starting in 2001, we saw a protocol called 6 to 4
Mm-hmm.
being used by adversaries to bypass our security controls. We saw it in 2008. We saw virus and malware actually include IPv6 CNCs
Mm-hmm.
by then. Up until Arbor Networks started supporting DDoS protection for IPv6, there was no detection for IPv6. That was 2017. So essentially, without the ability to see it, we have no ability to detect it. And that's that's a big concern. Is a lot of tools and a lot of people were just not prepared for it, but it's now.
So what you're saying then is that a lot of us, if we go back and take a look at our tools, whether we have a IDS or we're sampling packets or whatever, for the most part, we're tending to be looking at the IPv4. And in general, if we're focusing on that, we're not looking for IPv6. But for those who are kind of new to it, in a way, it's almost like making our devices bilingual. All right. If you have what we call a dual stack, I speak IPv4 and IPv6, I speak English, yo hablo español. I'm able to carry on a conversation in either language. But what if your security guards, if you will, our security infrastructure only speaks English? No habla español. Now you can start to understand where the potential issue may be for CISOs in that you've got a blind spot. And further, because that's going to be the default protocol that systems are going to use when they come online, unless you have actively disabled IPv6 in your enterprise, that is to say, gone to every last endpoint and turned that off, it's going to be kind of difficult to spot. So, what are your thoughts about? Well, first of all, what about that idea? Is that just kind of a goofy idea, turning off IPv6 everywhere? Because then, if you hear IPv6, you know it's an intruder.
Well, the cost of touching every device on an
Yeah.
infrastructure is very high to
Hmm.
turn IPv6 off. And there are applications and operating systems that if you turn it off, you must back everything up, reload the operating system, reload the applications. Therefore, now you could be talking 2 to 3 days for this particular component for on site systems. Um, so, this can be a real problem.
Yeah. So, what it sounds like then is that this is not a type of question that says, well, I'm just going to go ahead and keep hitting the snooze button on IPv6. We've been snoozing this for a bunch of years. And if you look at the adoption rate, of IPv6. So I remember back in 2013 when they passed 1%, and that was like a big deal. Today, what are we looking at in terms of the internet? And by the way, Google, if you type in IPv6 adoption rate into a Google search, it'll take you right to Google's page. What are we going to see there?
Right now, we see around 32% globally.
Mm-hmm.
Each country also has their own rating. As an example, India is either number one or number two with over 70%. And the reason is their country primarily uses mobility.
Mm-hmm.
And they identified that as long as we're using IPv6 on the mobility, V4 now, V6 in the future, or 4G now and 5G in the future, they simplify their operations for billions of people. So that's an issue. For the US, we were at 51, but the pandemic hit and people started turning it off. So we're down to 46, which is interesting. But it was interesting because when people are at home,
Mm-hmm.
we see a peak. When people go back to work, we see it decrease. So this really informs us that there's a lot of industry that hasn't actually moved to IPv6 and it may not even be prepared for it.
Well, that's an interesting data point because you can't really just order up a pandemic on demand to say, hey, let's go ahead and test our IPv6 adoption rate. But I know, for example, where I am here at home is that my ISP doesn't offer IPv6. And I'm thinking, like, really, guys? Well, okay, fine. I can roll with that for now. But businesses that don't offer it, then it either is a combination of ISP not offering it, or as CISOs or for our CIOs, we're just saying, I don't get this. It looks scary, and maybe I can just kind of avoid it. But I don't think we can keep avoiding it anymore. In fact, it's going to start to bite us pretty soon if we're not careful.
Can I mention something about this?
Certainly.
So organizations that I've assisted to support IPv6 only operations, some of the outcomes that we've had, the ability to identify malware on systems. If you're running IPv4, most malware are you're running IPv6 only, most malware is IPv4. So very quickly you can black hole that and you can shut down that system, you can shut down the switch for that port and send help desk out. That's a big advantage, number one. Number two, shadow IT.
Mm-hmm.
What is the real cost of shadow IT in your organization? Somebody can take a home router, plug it into your organization, have multiple systems, maybe even connected to some other network that you're just not aware of. You're not managing the security of those particular devices, and you don't even know that there's maybe malware on it or somebody's leaking data from it. So that's a big problem. With IPv6, each router has its own first 64 bits that are unique to that router. The interface that goes to the host on the switch for that specific subnet have a unique address for each of those. And by doing that, you now have end-to-end visibility internal to the organization for every device that's IPv6.
IPv6, right.
Now, what's real interesting is on the outside, we still have this problem where people want to use shared services. So they'll pay money to share, to run an application, to do whatever. With IPv6, every device on the outside, every cloud component, every Docker container on the outside has a unique IPv6 address. This gives you the ability to go end to end to say, should accounting be communicating with this nation state on this particular server or not? So I can now make different kind of decisions that we can't do with IPv4.
Interesting. So as we look at IPv4, let's kind of back down a little bit, and I'm going to play technical for a little bit because I do a lot of
Please.
network teaching and things such as that. So if we look at the Open Systems Interconnect stack,
Mhm.
the 7-layer model, as we call it, layer 1, physical, data, network, transport, session, presentation, application. And for those who know the extended OSI model, layer 8 is politics. But that's outside the scope of this talk. At layer 1 is a physical wire that we're actually moving information back and forth as a voltage. At layer 2, we're talking about the data link layer where we actually assign ones and zeros, and for the first time we actually have addresses. These are the MAC addresses that are burned in at the factory, and a switch, for example, is going to make decisions of where to send traffic based upon that layer 2 information or the MAC address. These are 48-bit addresses, and they are unique because if you had two devices with the same MAC address, you'd have some networking problems. So every manufacturer in the world is deconflicted through IEEE, keeping track of all of the organizationally unique identifiers or the OUIs, which is the first half of the 24 bits. I know I'm getting into some technical detail here, but for those who want to play the recording back, you can always get some more detail. At layer 3, which is what we're talking about, the traditional protocol that we've used for the internet is, well, the Internet Protocol, and in particular, IP version 4. There have been other protocols prior to IPv4, and we can talk about that in a moment, but I'm just kind of reciting the stack here. But IP allows us now to be assigned an address, unlike down at layer 2, where the MAC address is burned in at the factory. Think of it like a VIN for your automobile. At layer 3, it's like going to DMV and getting a license plate. You could take your car to a different state and get a different license plate, but the VIN never changes. And so therefore, our IP address, whether we're at home, at work, at an airport, a Starbucks, wherever we happen to be, is going to be dynamic, but it gives us the ability to communicate with systems around the world. And then when we get above that at layers 5, 6, and 7, where we're getting into the session layer, presentation layer, and ultimately the application layer, that's all about the protocol for keeping something going from the perspective of this is what the user sees, the session stays active, and we ensure that the character sets are transformed so that if you're big endian and I'm little endian, we're okay. But again, I kind of digressing into too much detail. But the real key here, where you get the opportunity to, if you will, start roaming around the world, is at this layer 3. And historically, it's been IP version 4. IP version 4 is 32 bits, and therefore 2 to the 32nd power of all possible addresses. And the kind of joke is that when Vint Cerf was kind of defining the internet as to what they thought, because, well, gee whiz, back then there's about 4 billion people on the planet and 4 billion possible addresses. And if this ARPANET experiment works out, gee whiz, every person in the world could have an IP address. Now, how many IP addresses do you have? I know in my home system here, I have to allow for at least 31 different systems, or 30, because my wife has all of her Alexa systems that we call it. And then there's Roku. My son comes down with his bunch of stuff. I've got my whole office network segmented, etc. And so we've got a lot of IP addresses. Well, what happened is what? In the early days of allocating internet IP addresses, they said, hey, you're a big organization. Have a Class A. What's a Class A? It means that of the 32 bits, the first 8 are assigned to you. That's like a country code. That's to say, hey, guess what? You're the United States, you're country code 1. You can be UK, you can be 44. All the other country codes get assigned. All right, great. How many IP addresses in a Class A? About 16 million. Wow. So that works for a really large organization. A Class B or Bravo network was 16 bits are locked down and 16 bits are free. That's more like an area code, using the analogy. And so now you get 65,000 addresses. And lastly, a Class C network would be 24 bits locked down, 8 bits to play with. 2 to the 8th is 256. But like I tell people, when you're trying to figure out how many network addresses you actually get, it's like a loaf of bread. If you've ever had kids or family members and you go to the bread and you find out they don't eat the end pieces, they skip and go right to the nice soft stuff in the middle. So when I want to get a sandwich, that's usually 2 end pieces with peanut butter on one piece and jelly on the other. And so we don't have a .0, we don't have a .255. Those get eliminated, and so therefore we get 254. Now, we got 4 billion, we'll never run out. But imagine if you bought toilet paper that way. Hey, I need a roll of toilet paper. Guess what? I've got a roll of toilet paper right here, sir. It's 254 sheets. Great, I'll buy it. Wait, I have a second bathroom. Well, I'm sorry, I can't sell you 2 sheets. You're going to have to go to Costco and buy a pallet with 65,000 sheets. But I don't, it's the next size up. Got it. But if I got a hotel, I need 100,000 sheets. Sorry, call Norfolk Southern Railroad. They're going to bring a car to you. It's going to have 16,777,216 pieces of toilet paper in it. Good luck with that. So pretty quickly, we figured that this Class A, Class B, Class C wasn't going to scale very well. So they then decided to issue what they call a classless or classless internet domain routing, or CIDR, pronounced as CIDR. Kind of reminds me of Rodney Dangerfield. Hey, call me when you got no class. In any case, the idea of a CIDR says that instead of having to pick a specific 2 to the 8th, 2 to the 16th, 2 to the 24th set of addresses, I could pick any power of 2. And as a result, I could slice and dice the internet address space into finer and finer chunks. And in doing so, we're able to extend the life of IPv4 quite a bit. But don't forget the ends of those loaves of bread. The smaller you cut the loaf, you still have 2 ends, the less efficient it is. And so we get to the point where trying to get an IPv4 address, we've run out in North America, we've run out in South America, we've run out in Europe and Asia and Australia. The only place left with unused IPv4 addresses, just a handful of them, is Afrinic in Africa. So that's not going to be a good vision for the future, because today, although there's 4 billion plus or minus possible IP addresses, the public ones, we're looking at about 13 billion devices. So what does IPv6 do for us that IPv4 does not in terms of address space?
To begin with, most companies get an allocation of /48, which is far bigger than they currently have. And some have 32, which basically means that organizations that get a /32 means that you have 4 billion networks, and each network can have to the 64th power of devices per network. So essentially, it's ultimately very, very scalable. And yes, that's in. If we were to name that particular addresses to the 128th, it in the undecillions.
Yeah. 3.3 times 10 to the 38th power,
Yeah.
undecillion. So a huge number. So what's the smallest address space that could be allocated? If I'm a home user and I say, hey, I want IPv6, do I get my one address like I have today?
No, it's real interesting. Some carriers are giving you a /64, which basically then allows you to put 2 64th devices on your system. A lot of companies are now realizing they want to give you a 56. Therefore, you have 8 bits
Yeah,
of,
just 256 times
yes,
that. Now, by the way, for those who are trying to do the math work in their head, 2 to the 64th power is 18 quintillion, or 18 446 more cat hairs than you have on your couch. And as a result, the home user gets that many addresses. Now, IPv4, they were handing them out like candy because it will never run out. But now they're, handing them out like candy again. But what we've done is we've added a huge multiplier, because one of the things that a lot of people don't do well is we don't think geometrically. We tend to think linearly. That's what life is like. And it goes back to the old riddle of, if you had a pond that was covered with lily pads and every day it had doubled, so each day the number of lily pads doubled. If on day 30 it were covered with lily pads, on what day was it only half covered? The answer is not 15. That's linear. It's 29, because the day before it was half covered. And now the next day, that half is doubled. And so therefore, what we're seeing then is a fantastic increase in the number of IP addresses, which, as a CISO, brings up an interesting question. How do you know it's on your network? Because you can't load it into a spreadsheet anymore. I have not found an Excel spreadsheet that has 18 quintillion rows in it.
yes. So there's a couple things that we do today. Old school IPv4 is we would statically address the devices, but that's a real pain to be able to touch, thousands of machines. We actually have two address mechanisms, and we can actually mix and match based on the operational needs of the business, which is pretty cool. We have something called neighbor discovery. Auto configuration is what it's also called. And what it does is it allows the host to ask for, hey, do you have a router on this network? The host basically says, oh, once it receives its network address, one or more, by the way, network addresses, so you have reliability, redundancy, and then it can generate its own last 64 bits. The biggest advantage there is very quickly you can lay up routers. Very quickly you can scale up devices on a specific segment. We also have DHCP. And DHCP works just like this. But unlike DHCP in IPv4, it doesn't require ARP. It's at the layer 3 level. Therefore, if I'm using cloud capabilities, I can communicate with layer 3. Most cloud doesn't allow you to see layer 2 at all. So therefore, I can set up a VLAN across multiple systems and be able to have multiple containers, multiple other systems, virtualizations out there that can all communicate with each other. Now we can mix the two depending on what the operation is. As an example, if I'm in a coffee shop, I can use their last 64, but I can create a completely random last 64 bits that can change on a regular basis while I'm at the coffee shop. What does that mean? Brute forcing the address is only temporary. The system all of a sudden changes addresses again. So all of a sudden now we have some additional capabilities that we didn't have before.
Sounds like frequency hopping. And it was interesting because I have a napkin, I saved it. So I was at a conference in Vegas years ago, and I remember, I think I'd heard about Hedy Lamarr, the
Yes.
actress who she had also done the spread spectrum, got a patent on it back in World War II. And she kind of lamented that people appreciated her for her looks and not her brains. In any case, I wrote down on the back of this Caesar's napkin, I still have it somewhere in a drawer, hey, why not do spread spectrum with IPv6, where you can go ahead and with each packet, or either have a predetermined sequence or encrypt the thing, and then it has the next IP address. So you're constantly going from a different IP address to a different IP address, and it's never the same pair ever, ever, ever. Well, Randy Marchini went out and built one of those things. Not because I suggested him, but with 7 billion people on the planet, other people are going to come with good ideas. So give him credit. And Randy's out there at Virginia Tech and has done some amazing things out there over the years. Great, great guy. And so, any case, what they did is they set up a camera, one of the campus cameras, and then you could also go to the site and you could see the frequency hopping. And there's a slight delay. They're still working on the performance on it. But the whole point is that if you were looking, and they have this wonderful graph, they just show things bopping, pop, 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 changing around. Imagine if you were up against an opponent and that opponent never ever used the same source and destination address twice. Does that complicate your data collection problem? Okay, now let's imagine for those of us who are CISOs that we are that opponent, that we are the target for some foreign collector or some corporate espionage or somebody who's trying to get our stuff. We all of a sudden now have with IPv6 some really amazing capabilities that were never available to us before. Now, Joe, you'd mentioned about neighborhood discovery. And one of the things that I think people find confusing when we first get into IPv6 is that there's different types of addresses. Now, in IPv4, we have public addresses, and there's RFC 1918, which sets aside the non-routable addresses, the 10 dot something, 192.168 dot something, and 172.16 through 31 dot something. Okay, fine. We understand that those are used internally. Most of our CISOs and most of the people listening on the broadcast understands that. But how is that translated over into IPv6? And do you actually get a third type of address?
Well, actually, we have Unicast, Multicast, and Anycast. That's the one focus. Unicast, we want point-to-point communications. Multicast, we can use the router to communicate a single packet and have it replicated to authorized endpoints, both on our segment and across our operation, which is pretty cool. We have Unicast where a device can have the same address like your DHCP. So every device can have a same exact DHCP address, and whichever one's closer, it actually queries and pulls the address from. This the second component is we have link local addresses. We have addresses that FE80 addresses. FE80 addresses are real nice because if your application says, if there's a device on my segment, I will only communicate across that network segment. That traffic does not leave that particular segment. That's a big advantage, especially for things like Docker containers. The sidecars for Dockers. It's very important for things like zero trust. So you have all these additional features. Then we have the ULA, which is just like RFC 1918. It's used in special cases.
And so ULA is unique local address,
Yes.
okay? And that's an address that's going to begin with FD or Foxtrot Delta as the first two hex characters. Sorry, I just want to make sure I threw that in there for everybody.
Yes. So you can choose to use this or not use this. There are several papers out there that help businesses identify when it makes sense and when it doesn't make sense. So there's a lot of people will, as an example, set up their labs when they're prototyping IPv6 so they can use that to see how does the routing work, how to host, how does their containers, their virtualizations, Kubernetes works, things like that. Kubernetes, by the way, supports IPv6. And then you have your global address. And those global addresses are really interesting because they start with a 2. And the reason they start with the 2 is we've allocated other blocks. Publicly, that's because we don't need all those additional addresses. Privately, there's a discussion that maybe there's a block set aside for the moon. Maybe there's one for Mars, but that's a whole nother discussion. After that, it's whoever the RIR is, the regionally registry. They have their own codes, which, depending on the bits, you can actually look at the address and say, oh, that's from Apnic, that's from Aaron, that's from whatever. So from a geolocation, from whatever, it gives you an indicator. After that, there's a set of bits that are allocated by your carrier or to your carrier, and then there's another one that your carrier can allocate. So essentially, you can then take those carrier addresses that you can define, and you can say, oh, this particular hex character is Philadelphia. This one is Georgia. This one is whatever. And then the next character can be used for this is accounting, this is business, this is whatever you want to actually define. So we can now encode specific information into those addresses for two reasons. Number one, we have the ability to summarize the addresses, so we optimize the routing between locations. The second thing that we have is the ability to provide more information, because obviously this wouldn't be published, more information to your SOC and your NOC, so they can actually identify very quickly, hey, this particular system, this particular function, this particular router is either down or it's being attacked. So this becomes a real advantage to say, oh, this is owned by so-and-so. I can look that up through something called an IPAM, IP Address Management Program. Very important to look at. There's both commercial and open source, but that's beyond the scope of the details.
Right, because Excel is just not going to cut it.
Oh, no, it's not. Then the last 64 bits, we define that again based on the business need. You may have IoT devices out there. You may take a /64 and define it for my IoT devices for all the cameras in your network. All those cameras can be on the same VLAN. They can be, customized to do different things. But by having that, now I can go to that subnet and be able to, that's 64-bit, and be able to see each of those data streams if you need it, which is pretty cool. So that's actually a big operational advantage of
So,
having that component.
so you've got all these IP addresses, and we're actually using them intelligently. It's not just a throwaway, but there's ways that we could tag intelligence into the IP address space, something that we haven't really done in the past because there just wasn't enough maneuvering room for it.
Can I give you an example?
Sure.
So I set up a web server. What do I have? I have port 80 open, maybe or maybe not. I have 443. I have maybe 22. I may have a dozen other addresses or a dozen other ports open. So an adversary identifies that a single device exists. What's the next thing they do? They port scan that specific address. Boom, they're there. They now have it fingerprinted. With the addresses, I can take SSH and put it on a different address for that specific device. Okay, I can have a Docker container and have a Docker container where it's communicating with a database or whatever, but the management interface can be on a separate address. So by doing this, we make it more difficult for the attacker to deal with it. Plus, with the additional addresses, as we see scans, we can then choose, do we stop those scans? Do honeypots suddenly show up in front of them? Or do we allow them through? Those are decisions that we can make that we cannot make with IPv4.
So what we're doing is we're decoupling the control from the function, in that we can now say, with all these addresses available, we don't have to shell out a lot of money for them because they're publicly facing if you want to be internet facing. Quick aside, so when my son was down visiting, he'd set up a Raspberry Pi, and he had made it publicly exposed. Then you go there and port 22 SSH, and he was smart. He set up some good keys and things like that, so it was cryptographic keys. Well, I went ahead and took a look at my connection logs, and it lit up like a Christmas tree. And all these connection attempts trying to hammer into port 22, coming from Eastern Europe mostly. And of course, they don't know that it's a Raspberry Pi. They figure maybe it's a bank with $1 billion behind it. But now what you're saying is that I can expose a service to the internet on an IP address and have all the control functionality someplace else entirely, essentially making it so that attackers are really stymied, and they're not going to try to go through 18 quintillion addresses just trying to guess.
And honestly, I have servers that have been out on the internet for 5 years. They've never been scanned for IPv6. I put several out there and was as noisy as possible. Yes, I got scanned, but I was able to identify that particular scan. So the gray noise that we have on IPv4 is gone unless an attacker is looking to compromise your particular infrastructure. That for me, that is a very promising opportunity to be able to focus on the security of systems, to be able to identify that an attacker is interested in, they have intent, and to be able to make a choice of how you're going to shut them down or lead them someplace else.
Pretty cool. Now, we got about 5 minutes left in the show, but I know one of the things we've talked about in the past is the idea of geolocation with IPv6 and somebody trying to pretend to maybe be somebody they're not. What are some of the advantages or even disadvantages out there? That is to say, we joked one time about you having found somebody said, your IPv6 is showing, because they kind of gave away their location.
Yeah, so from a geolocation, a lot of the commercial companies, actually, we had this discussion when I was running Disrupt 6. I basically set up a company at the same time Gmark did. His card kill, which was awesome idea.
I think
Still is.
I think we're both about 7 years too early for
Exactly,
our ideas.
exactly.
It was 7 years ago we did it. Now both of these things are going huge. Anyway, continue.
Yeah. So the ability to be able to know what continent something's from, to be able to know what carrier it's from, to know what cloud provider it's from, where the location from that cloud provider gives us a lot more information than we could ever imagine with IPv4. As an example, you put up a tour, you have IPv4, there's IPv4 addresses are limited, but they change them on a regular basis, whatever. With IPv6, they're going to get a /64. So instead of actually blocking the 128, we go, oh, you silly person, and we drop 64. If they come back from an address that's larger, we drop a, you know, 48. We drop a 32. And essentially, they then have to go find a new place to pivot from. So again, we have better defenses.
So you're able to basically blind the bad guys, so to speak, and make it harder and harder for them to find a launch point for their attacks.
And I like that,
I
don't
know.
you?
I love that evil laugh.
Yeah.
Joe is known for his evil laugh and ability to do things such as that. So yeah. So what we find then is that with IPv6, what we're able to do is really kind of have a little bit of a game changer. We're no longer going to be constrained in terms of having limited. I remember for a while they were giving away IPv6 just to kind of get people online. Now I think or basically ISPs aren't as generous anymore. But the point is that if you're not doing IPv6 in your enterprise, or more precisely, if you are doing IPv6, but you as a CISO, as a security expert, are not proficient in it, add that to your homework list. Please get good at this. This is going to become definitive coming up in the next year or two, if not already. And it's going to make a huge difference in whether or not you're going to be successful in identifying and potentially blocking attacks and protecting your enterprise, or something getting in undetected, achieving a huge amount of damage. And then you've got to explain to your boss or the board what happened.
Can I make a comment? A lot of nation states have decided that they're moving to IPv6 only very quickly. As an example, OMB 21.7 finds completing IPv6 deployment. 80% of the federal government, the executive branch, will support IPv6 by FY 25. And what is that? That's pretty quick. And we're also seeing other nation states talking about exactly the same thing. Portland is doing the same thing. Seattle's doing the same thing. So cities are doing exactly the same thing. So to maintain connectivity, communications to the people you do business with, the people you communicate, the email, everything else, you really need to look at this, because you don't want to wait until the last minute. If you don't prepare to move to IPv6, making sure your products support IPv6, things like that, IPv6 only operation, it can cost you a lot of money to make that move, and therefore making both security and operations far more expensive.
And meanwhile, your competition is doing it, and they're taking away market share.
That's already happening. Have you heard of a company called Wells Fargo?
I have, but we're down to about the last few seconds of the show, so we'll have to say that for another time. But hey, it's been my privilege, Joe, to have you with you on CISO Tradecraft. Hopefully, you've enjoyed listening to a master, an expert who really has known an awful lot. And I've had the privilege, Joe, 20 years or so, and it was great to have him on the show. If you've got questions, if you have anything you'd like us to follow up on, please send us a note. Don't forget to follow us on either LinkedIn, if you're on LinkedIn, or come to our CISOTradecraft.com and make sure that you tune in for the latest episode. This is G. Mark Hardy. I'm here with Joe Klein, so I thank you very much for listening to another episode, and we'll look forward to being with you again soon.